Hello, my name is Dr. Chris North. I'm an astronomer in the School of Physics and Astronomy at Cardiff University. And I want to tell you today about how we really know that black holes exist. Black holes came from a theory of Albert Einstein's. He came up with his theory of general relativity in 1915. But it was actually other scientists, Karl Schwarzschild being one of the first, who solved his equations and showed that if you had a point mass that was dense enough, you got this unique situation where you had a singularity, and almost an infinitely dense point in space. And that meant it had some bizarre and unusual consequences. Most notably, there was this surface beyond which nothing could escape, not even light. Something called the event horizon of a black hole. Now, that's not actually a new imagining. That's actually not a new concept. You can imagine taking what you might call an everyday object, a planet or a star or something that we know about already, even before Einstein's theories. Taking something like the Earth and compressing that down, so keeping its mass the same but compressing its volume down. If you did that with the Earth and you compressed it down to a radius of instead 6,000 or so kilometers down to about 9 millimeters, so just under a centimeter radius, then its density and its mass and its size, and therefore its density, will be such that on its surface, the escape velocity required, that's the velocity to fully escape its gravitational pull, would be faster than the speed of light. So nothing, not even light, the fastest thing we know about, of course, could escape. So they were a mathematical curiosity for a long time, and there was debate about whether they actually existed. And it was really in the 1960s and 70s when astronomy really had a bit of a boom in discoveries for a couple of reasons. One was radio astronomy really coming to its fore since its sort of invention, if you like, in the 1930s by a radio astronomer, the father of radio astronomer Karl Jansky. And then also X-ray astronomy. So it was really the early days of X-ray astronomy, but starting to look at specific objects in the sky, very bright objects in the sky. And one such object was an X-ray source in the constellation of Cygnus, called Cygnus X1, about 6,000 light years away, and known to be a star, quite a bright, massive star, quite a big star, a red giant, if you like. But it was emitting X-rays, and that meant that instead of being a star there that was thousands, maybe tens of thousands of degrees on its surface for a hot star, this thing was emitting things at millions of degrees, or had a characteristic temperature of millions of degrees, which a normal star has no business doing. So what could it be? Well, the interpretation was that there was a companion, there was another object with this star going round it in an orbit, some kind of binary system, that was emitting these X-rays, called them X-ray binaries. And then when you study the X-rays in the 1960s, it was deduced that the X-rays were varying very, very quickly. And they were varying on such a time scale that it implied the object had to be very small. If it was much bigger, then to vary on those time scales, well, if it was too big, then light would take longer to travel across the object, and so it couldn't vary on such fast timescales. So actually, the timescale of variation of objects tells you a limit on it, a constraint on their size. And it was deduced that this thing was less than maybe 100,000 kilometers across or thereabouts, which is smaller than the sun. And yet it was also known that this thing had a mass, from looking at the orbit, of maybe 15 times the mass of the sun. So you can't imagine a star 15 times the mass of the sun, but a fraction of its size, maybe a tenth of its size or thereabouts. The fact that it had very strong X-rays meant that this could be an unusual object called a neutron star, which is what happens when a star much more massive than the sun dies, comes to the end of its life. This is something that had been deduced in the early to mid 20th century, what happens when massive stars die. And as they die, they collapse under gravity, and they end up, if they're in the right mass range, of making this stable object that's almost like a giant atomic nucleus about 10 or 20 kilometers across, called a neutron star. But if we think that there's a maximum mass they can be of about 3 solar masses, 3 times the mass of the sun. And so if the star is much more massive than some threshold, when it collapses at the end of its life, when it runs out of fuel, it smashes through that neutron star threshold, if you like, and everything collapses even more to an even denser object and ends up forming it so closely packed together. It reaches that point at which the escape velocity is faster than the speed of light, and you have a black hole. That's how we think these black holes are formed. And the fact that there was something that was 15 times the mass of the sun and was but there didn't seem to be any normal sort of optical light coming out of it. And this thing probably had to be a black hole for various reasons. Now, the light we're seeing in X-rays from this thing are not coming from the black hole itself. Black holes don't emit light. That's why they're black. Nothing, not even light, can escape, of course. It's because this is in a binary system, the larger object is having material pulled off it by its gravitational pull, and it's going to orbit around the black hole. Now, as that gas goes into orbit around the black hole, it reaches very, very high velocities, and the collisions between the molecules of gas and the friction, if you like, causes it to heat up to very high temperatures. That will also cause it to spiral inwards, and some of it will get absorbed into the black hole. Lots of it will stay in that orbit for quite some time. But that's what's causing the X-rays to emit, and that's the thing that's got this very small size. The black hole itself is really tiny, right in the center. So that was one source that maybe these things were real. But the reasoning for it being a black hole was more that we couldn't think of anything else it could be, which isn't really very satisfactory from a scientific point of view. So what about other types of black holes? Well, there's another class of black holes called supermassive black holes. These are objects that we now know lurk in the centers of all, certainly most, if not all, large galaxies, including our own. These were seen, again, in the 1960s and 70s in the form of an object called quasars. These are, it's a shortening of quasi-stellar objects, very bright objects that, when you look through a powerful telescope, look like a star. They're pinpricks of light, so they're not diffuse like a galaxy. They're much, much smaller, and yet are very bright. There were theories that maybe these are supermassive stars. Maybe these are stars millions or billions of times the mass of the sun, but theoretical predictions were that that's not stable, that they would collapse under gravity and form a black hole. It's now known that, in fact, what we're seeing with quasars is, again, like that X-ray binary system, a cloud of material around a black hole that's emitting, it's getting to very, very high temperatures and emitting strong radiation. In fact, sometimes that material goes around, as it spirals in towards the black hole, some of it ends up being kind of funneled into jets that come out of the poles of the black hole system. And so that's something that we think is happening with a lot of the quasars. We're looking down that jet of material that's coming back towards Earth. And the reasoning for thinking that they're black holes is that, again, they are small enough, they are so small and so massive that you can't really think of anything there is. There's one in the center of our galaxy, and the observational evidence for that, it's hard to get. We can't see it with optical telescopes because there's too much galactic dust in the way, blocking our view. But with infrared telescopes, we can look at the motions of stars in the center of the galaxy, and they're going around an object. And the way they're going around the object, you can just use, basic laws of gravity from hundreds of years ago to say, well, if the way they're going around tells us what the mass is of the thing that they're orbiting. And it turns out it's about 4 million times the mass of our sun. And we knew that the upper limit was that it had to be smaller than our solar system, which means that, again, there's something smaller than our solar system that's 4 million times the mass of our sun and not emitting any light itself. The only thing we can really think of is a black hole. So that's great. We've got, again, more evidence of, well, we can't think of anything else it can be, but we really want to have a testable theory that is, well, if it is a black hole, there should be this certain property. And one of the observations last year, in fact, from a telescope called the Event Horizon Telescope, looked at a supermassive black hole right in the heart of a relatively nearby galaxy, a few tens of millions of light years away, called Messier 87, M87, a very massive galaxy with a black hole billions of times the mass of our sun right in its center. And the observation showed that you could see a ring of material around a very, very small object. They got that at very, very high resolution by combining telescopes around the world, looking at millimeter wave radiation. And in the center, you see a hole, you see a gap, and that's the black hole itself. That's like the silhouette of the black hole. Anything that gets closer to it than that essentially gets pulled inwards into the black hole. And you see distortions in that ring that agree with the predictions of general relativity, of Einstein's theories and later solutions to it. So again, that meets that satisfies that argument of, well, if this is a black hole, we should see this, and that's what we see. So then we know it's a black hole. It really is a very, very small object. There's one final test, which of course is looking at the native properties of black holes. So black holes are very, very pure objects. They are, in some senses, the most pure, the most basic object that we know of. They have 2 or 3 properties. One is they have a mass. so we can measure their mass. They have a spin. We think the black holes are spinning, just like pretty much everything is out in the universe. And then finally, they probably have an electric charge, which is just the accumulation of all the things that they've swallowed, if you like, over the billions of years. If that's had an electric charge, that will add up. It probably averages up, because you have positive and negative charges. They probably pretty much cancel each other out, so you're getting a net zero charge on the in total. But that's the three properties: mass, spin, and possibly charge. It's actually something called the no-hair theorem. They're no more complex than that. So that means, apart from looking at their effect on other objects, on their effect on the material around them, the only way to observe the black hole directly is because it is through its mass, its gravitational interactions. And a black hole is just sitting there. It doesn't do much gravitationally apart from have an effect on the stuff around it, until you get two black holes. When you get two black holes going around each other, if they're close together and they're orbiting, they create ripples in the fabric of space. They're both distorting space because of their gravitational pull. That's what Einstein's theories of general relativity said. And when you get two moving around in a particular way, then they cause ripples in space that spread outwards. It's a bit like if you imagine twirling a stick in a pond, you get ripples coming outwards in sort of spiraling outwards. And so these gravitational waves, these ripples in the fabric of space, spread out through the cosmos. They spread for billions of years. They get weaker and weaker as they go, and they're already incredibly weak. But we have sensitive detectors here on Earth, gravitational wave detectors, LIGO and Virgo, and now coming online, the Kagra detector in Japan. And those detectors are able to pick up the unique signature of two black holes spiraling in and merging. And that lets us test that theory of when these black holes are essentially touching, and to really test Einstein's theories of relativity and the solutions to that are about black holes really to their limit. So from the mathematical curiosity of there could be this particular type of object, to finding these X-ray binaries of binary stars going around each other, or binary stars with one being a black hole, to supermassive black holes at the hearts of galaxies, which we've now imaged using the Event Horizon Telescope, and to the gravitational wave detectors that colleagues here in Cardiff are so heavily involved in, looking for the signature of pairs of black holes spiraling in and merging. There really can be no doubt anymore that black holes really are real.